Section 1.2, Gaussian Elimination. To be of reduced row echelon form, a matrix must have the following properties. 1. If a row does not consist entirely of zeros, then the first non-zero number in the row is a 1. We call this a leading 1. 2. If there are any rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix. 3. In any two successive rows that do not consist entirely of zeros, the leading 1 in the lower row occurs farther to the right than the leading 1 in the higher row. 4. Each column that contains a leading 1 has zeros everywhere else in that column. A matrix that has the first three properties is said to be in row echelon form. Thus, a matrix in reduced row echelon form is of necessity in row echelon form, but not conversely, so it doesn't necessarily work the other way around. As an example, let's look at these matrices over here. Notice that they are in reduced row echelon form. They have these leading 1s for each of their rows that have non-zero entries. They have rows that consist entirely of zeros on the bottom. They have successive rows that do not consist entirely of zeros, where the leading 1s are further to the right, the farther down you go. And in each column that contains a leading 1, there are zeros everywhere else in that column. So notice all of these zeros over here, these zeros over here. The leading 1 is the only number in the column with the zeros. Notice over here we have these matrices in row echelon form, because notice the only difference is that over here we have a 4. To be in reduced row echelon form, it would have to be a 0. Over here we have this -3 and 6. Those would also have to be zeros. This one would have to be 0. But because we have zeros underneath, we're still in row echelon form. With any real number substituted for the stars, all matrices of the following types are in row echelon form. So you could put any numbers over here for any of these guys, and they'll all be, well, not for that one, they'll all be in row echelon form. To be in reduced row echelon form, these guys would have to be zeros because they're above 1. These wouldn't have to be zeros because it's above a 0. Notice over here, these are in reduced row echelon form. These are the zeros instead of those stars, like I mentioned. You could still have any number over here because it's not above the leading 1. Over here, that would have to be a 0, etc. As another example, suppose that the augmented matrix for a linear system in the unknowns x1, x2, x3, and x4 has been reduced by elementary row operations to this matrix over here. Let's solve this system. Well, notice that each of these numbers is the coefficient of one of these variables. Our first column is the x1, second one's the x2, the x3, the x4, and what it equals. So that means that over here we have 1x1 plus 0x2 plus 0x3 plus 0x4 equals 3. So it's the same thing as just saying that x1 is equal to 3. Over here we have 0x1, but we have 1x2. So we have x2 plus 0x3, 0x4 equals -1. Then over here we have 1x3, 0 of the other one, so x3 must be 0, and similarly x4 must be equal to 5. So that means our solution to our system is x1 equals 3, x2 equals -1, x3 equals 0, and x4 equals 5. That's the same thing as writing the ordered 4 tuple. Oops, I wrote 4 because I said 4, but it's really 3, -1, 0, 5. The variables that correspond to the leading 1s in a matrix in reduced row echelon form are called leading variables. The remaining variables are called free variables. So in this case, all of these variables were leading variables because they all corresponded to leading 1s. In each part, let's suppose that the augmented matrix for a linear system in the unknowns x, y, and z has been reduced apply the elementary row operations to the given reduced row echelon form. Let's solve the system. So for our first one, we have, let's see, looks like we have x equals 0 for the top, y plus 2z equals 0 for the bottom, but for the second row, but for the bottom, we have 0x plus 0y plus 0z equals 1. Which is the same thing as just saying 0 equals 1, which is false. So this system is actually called inconsistent. There is no solution. Let's look at the second one. Again, it looks like we have a bottom row with a bunch of zeros. However, in this case, it's 0x plus 0y plus 0z equals 0, not 1. So that's a little bit better. We also on the top though have x plus 3z equals -1. For our second equation, we have 0x plus 1y minus 4z equals 2. So notice in the bottom equation, we don't really have any kind of contribution here. So let's just solve these two. If I take both equations and try solving for x and y, I would get x equals -1 minus 3z, and I would get y equals 2 plus 4z. So notice there is no leading 1 for z. We just have a leading 1 for x, a leading 1 for y. So z is a free variable. Whenever we have a free variable, what we can do is write it as a parameter. We just make up some other letter, we let the free variable become that parameter, and we'll write our variables in terms of that parameter. So in this case, our parameter, we could just make it t, for example. So how about x equals -1 minus 3t instead of z? We'll set y equal to 2 plus 4t, and then we'll just set z equal to t. Notice that this gives us an infinite number of solutions. We can set the t, which is the z, equal to any real number, and we'll get a different solution. For example, t equals 0. That would give us -1 minus 3 times 0, so x would just be -1. Y would just be 2 by plugging in 0 for t, and then the z, of course, is t, so that's 0. We could also, for example, take t equal 1. That would give us x equals -4, y equals 6, and z equals 1. Again, there's no special numbers here with 0 and 1. We could have chosen anything to demonstrate the infinite number of solutions here. Let's look at our last one. Notice we have 2 rows of zeros this time. So let's focus on our first row. Notice this is also going to give us 2 free variables. We'll have there's no leading 1 for y, there's no leading 1 for z, so we'll have y and z as free variables. We just have the leading variable x, so we'll have 2 parameters. So we'll have x minus 5y plus z equals 4. We'll solve for our leading variable, and we'll get x equals 4 plus 5y minus z. We'll set, how about y to be s and z to be t, so we'll get x equals 4 plus 5s minus t, and we'll have y equal s and z equals t, and that's our solutions. We could set s and t to be any real number, and we'll come up with another solution. If a linear system has infinitely many solutions, then a set of parametric equations from which all solutions can be obtained by assigning numerical values to the parameters is called a general solution of the system. The following step-by-step elimination procedure can be used to reduce any matrix to reduced row echelon form. First, we'll locate the leftmost column that does not consist entirely of zeros, then we'll interchange the top row with any other row if necessary to bring a non-zero entry to the top of the column found in step 1. The idea is that we want to try to get a leading variable. Like if we had 0 as our first row, we would have just swapped it to get the 1 up over there. After we do that, if the entry that is now at the top of the column found in step 1 is A, we'll multiply the first row by 1 over A to introduce leading 1. So for example, if you had a 5 over here, you would just divide by 5. Multiply by 1/5, same thing. And that way you get a 1. So we're basically just trying to get a 1 on the top left. Then we'll just add suitable multiples of the top row to the rows below so that all entries below the leading 1 become zeros. So we'll do whatever we need to do to cancel out the numbers underneath that leading 1 after we introduce it over there. We'll then cover the top row in the matrix and begin with step 1 applied to the submatrix that remains. Basically, once we get a 1 over here, we're going to do the exact same thing to get a 1 over here. Once we do that, we'll try to get a 1 over here. If it's not possible, like with this, 2 rows of zeros right over here, then we just stop and we're in reduced row echelon form. That is provided that we've done the last step of adding suitable multiples to each row to introduce zeros above the leading ones. Like if we had over here is a good example. If we have a leading 1 over there, then there has to be a 0 on top. So what we can do is add multiples of this row if there happens to be some other number over here in this row up top, and we can get rid of that number. This procedure or algorithm is called Gauss-Jordan elimination and consists of 2 parts: a forward phase in which zeros are introduced below the leading ones, and a backward phase in which zeros are introduced above the leading ones. If only the forward phase is used, then the procedure produces a row echelon form and is called Gaussian elimination. So how about we do an example of that? Let's solve this system by Gaussian elimination. So what we'll first do is we will write the system as a matrix. So let's see, we've got 1 for x1, 3 for x2, minus 2 for x3, and so on. So I'll just try to write that out. 0, 2, 0, 0. And the next row is 2, 6, negative 5, negative 2, 4, negative 3, negative 1. Then we've got 0, 0, 5, 10, 0, 15, 5, 2, 6, 0, 8, 4, 18, and 6. And I think that's our entire matrix. So how about we try to take row 2 and let's try to eliminate that 2 right over here. At the same time, we could also eliminate this 2 over here in the last row. It looks like all we have to do is take the top row, multiply by negative 2, and then we can add it to each of these rows and it'll cancel them. So how about I write that I'm going to set row 2 equal to row 2 plus negative 2 times row 1. And at the same time, I'll set row 4 equal to row 4 was before plus negative 2 times row 1. Usually I'm not going to write out these steps like this. I'll just, write out the final answer, but I want to show you what's going on very explicitly. So I'll have the exact same top row as before because I already had the leading 1 there. I didn't have to do anything. So I'll just rewrite that. However, it looks like my next row now no longer has a 2 over there. So I did negative 2 times the 1 and I added it. I got 0. But if I do negative 2 times 3 and add that to 6, then I get negative 6 plus 6 is also 0. If I do negative 2 times negative 2, then I get 4 plus negative 5 is negative 1. It's just going to be 0 plus negative 2, so that'll stay 0. And then this becomes negative 4 plus 4 is 0. This, both of these are just adding 0, so negative 3 and negative 1 remain. I didn't do anything to row number 3, so we'll just copy that. 5, 10, 0, 15, and 5. And then my last row, I also eliminated some stuff. The 2 and the 6 get eliminated the same way as above. Negative 2 times negative 2 is 4, plus 0 is 4. And then 0 plus 8 will just stay 8. This is going to cancel the 4 the same way it did before. And then these are going to stay 18 and 6. Okay, so we've made some progress. Now we have zeros under the first leading 1. Let's see if we can try to get another leading 1. We could probably get one right over here if we just multiply row 2 by negative 1. So let's set row 2 equal to negative row 2. And then we'll have a leading 1 over there. At the same time, we could eliminate the 5 and the 4 by adding multiples of row 2 to them. So how about, after we make this negative, this will become a positive 1. So let's multiply it by negative 5 to eliminate the 5, and multiply it by negative 4 to eliminate the 4. So we will set row 3 equal to row 3 plus negative 5 times row 2. And we'll set row 4 equal to row 4 plus negative 4 times row 2. So let's see what our matrix becomes. Top row I still haven't changed, because once I have that leading 1 there, I'm pretty much good for now. So 0, 2, 0, 0. My second row, all I did was make it the negative version of itself. Now I have my leading 1 there. Everything else changes sign. And my third row, oh, well, that's actually really cool. If I take 5 times this thing, notice it's going to cancel with this, just like I wrote, but 5 times this will also cancel this. I'll get 0 there. And then, of course, 0, 0 stay. 5 times 3 is 15, so all of these guys become 0 when I add 5 times the second row, or negative 5 times the new second row. Well, that's pretty cool. Notice I get something similar with my fourth row, because this will cancel this when I multiply it by 4. This will cancel this. This will stay 0. But 4 times 3 will just give me 12, so this will become a 6, and this will become a 2, because they'll become 4. So it looks like I get 0, 0, 0, 0, 0, 6, 2. Alright, pretty cool. Let's keep moving on. It looks like we got a row of zeros. So as we said, that has to go on the bottom. So let's swap rows 3 and 4. While we're doing that, how about we try to get a leading 1 in the new row 3. So we'll just divide that by 6, aka multiply it by 1/6. So we'll set row 3 equal to 1/6 times row 3. So we'll get 1, 3, minus 2, 0, 2, 0, 0. We'll get 0, 0, 1, 2, 0, 3, 1, just rewriting, but now our new row 3 will be 0, 0, 0, 0, 0, 1, because we multiply by 1 6, divided by 6, and then 2 times 1 6 is 1/3. And we'll have our row of zeros in the bottom. Okay, so we're making great progress. Now we're in row echelon form because we have our leading ones in each row. We have our row of zeros in the bottom, but we wanted to get to reduced row echelon form. So what we'll have to do is we'll have to get zeros above our leading ones as well. This is like our, we did the forward phase, now we're doing the back phase. So how about we take row 2 and we can add -3 times row 3 to cancel out this 3. And we could take row 1 and add 2 of row 2 to it to cancel out that -2. So row 2 will be equal to row 2 plus -3 times row 3. And row 1 will be row 1 plus 2 times row 2. So the new row 1 will be 1, 3, because there's just zeros over there. We don't have to worry about that. But we'll get a 0 over here because we're adding 2 of these guys to it. So we'll get 4, because now this 2 is going to have to multiply by 2 and add over there. 0 won't contribute anything, so we'll keep our 2. And then -3 will cancel over there. Notice I'm getting a little bit ahead of myself here because I'm already anticipating this becoming a 0. But this will be 0, and when this gets multiplied over here by -3, then it'll cancel this guy too. So I won't have to worry about having to change these. All right, why don't I show you what the new second row becomes? It becomes 0, 0, because row 3 has these zeros over here, won't contribute to anything. In fact, none of these will change, so none of these will change it. So we just get 1, 2, 0, and this 1 times -3 cancels this out, gets me 0, and then 1/3 times -3 will cancel this guy out and give me 0, which is why if I do the row 1 change after doing the row 2 change, then I don't have to worry about these last 2 over here. Just a little bit easier. And let's see, I left row 3 alone, so I'll just rewrite that. 0, 0, 0, and 0, 0, 1, and 1/3. And then all my zeros in the bottom. And now we're in reduced row echelon form. Wonderful. So we can just read off our solution to this thing now. Let's see. We have, how about x1 plus 3x2, where is it, 4x4 plus 2x5 equals 0. I didn't leave myself very much room, but I think I could still make it work. x3 will be plus 2x4, and that's it for that row, so that's 0. And then I've just got 1 x6 equals 1/3. Okay, nice. So that means that I can solve for my leading variables. Notice that would be the x1, because that's the leading one, the x3 for that, and then the x6. So I'll get x1 equal to -3x2 minus 4x4 minus 2x5. And I'll get x3 equal to -2x4. And I'll get x6 equal 1/3. I want to parameterize my free variables, which are all the ones that are not leading. So I'll make, how about x2 equal to r, and then x4 equal to s, and then x5 equal to t. So that would make x1 equal to negative 3r minus 4s minus 2t. x2 I said will be r. x3 will be negative 2s. x4 will be s. x5, my other free variable, my last one of the three, will be t. And then x6 is still 1/3. And that's my solution. Let's move on. A system of linear equations is said to be homogeneous if the constant terms are all 0. That is, the system has the form over here where all of our constants are now 0. All these guys. Every homogeneous system of linear equations is consistent because all such systems have x1 equals 0, x2 equals 0, and so on to xn equals 0 as a solution. This solution is called the trivial solution. If there are other solutions, they are called non-trivial solutions. Because a homogeneous system of linear equations always has the trivial solution, there are only two possibilities for its solutions. Either the system has only the trivial solution, or the system has infinitely many solutions in addition to the trivial solution. As an example, let's use Gaussian Elimination to solve this homogeneous system that is very similar to the one that we did in example 5. In fact, it looks like it is the same except that we're now equal to 0. So first we will write it out in matrix form. So we'll rewrite the coefficients. 1, 3, minus 2, 0, 2, 0, 0, 2, 6, minus 5, minus 2, 4, minus 3, minus 1, 0, 0, 5, 10, 0, 15, and 5, and 2, 6, 0, 8, 4, 18, 6. Okay, so what we'll do is we'll put that in reduced to echelon form, but that should be easy enough because we basically already did it. The only difference is that it won't equal what it equaled last time. Our last column will change to zeros. You could verify it by doing the exact same steps again, but it won't make any difference. So we'll just put everything the same, except that we're going to change our last column to zeros. So instead of this thing equaling 1/3, we'll just make it equal 0. And then our last row is already all zeros. Okay, good. So let's see. That means that we have x1 plus 3x2 plus 4x4 plus 2x5 equals 0. We also have x3 plus 2x4 equals 0. This time x6 equals 0. And I think that's about it, because the last one is just 0 equals 0. I don't need it. So solving for our leading variables, we get that x1 is negative 3x2 minus 4x4 minus 2x5. We get that x3 is negative 2x4. And we get that x6 is 0. So again, we'll set our free variables into r, s, and t. So we'll get x1 equal to negative 3r minus 4s minus 2t. We'll get x2 equal r. We'll get x3 equal to negative 2s. And we'll get x4 equals s, x5 equals t, and x6 equals 0. Almost the same as before. Next up, the free variable theorem for homogeneous systems. If a homogeneous linear system has n unknowns, and if the reduced row echelon form of its augmented matrix has r non-zero rows, then the system has n minus r free variables. Should kind of make sense that you'll end up with the free variables for your 0 rows, you know? A homogeneous linear system with more unknowns than equations has infinitely many solutions. That should also make sense, because if you have a whole bunch of unknowns but you have a limited number of rows, then you're going to have a whole bunch of free variables, which could equal anything, which will just give you tons of different solutions. For large linear systems that require a computer solution, it is generally more efficient to use Gaussian elimination, followed by a technique known as back substitution to complete the process of solving the system. So how about we take a look at this next example. From the computations in example 5, a row echelon form of the augmented matrix is given over here. Let's solve the corresponding system of equations. So we'll do this back substitution technique and illustrate the difference. So it looks like we do not have reduced row echelon form, because look at, we don't have zeros over there. So we basically have the forward part but not the back part, so we'll do back substitution to finish this up. We'll write out the x1 plus 3x2 minus 2x3 plus 0x4 plus 2x5 plus 0x6 equals 0 from our top row. Then x3 plus 2x4 plus 3x6 from our second row. And then x6 equals 1/3. So it's basically like example 5, except we stopped before finishing solving it so that we could do this alternative method of finishing it up. So we'll solve for x1. We'll get that x1 is negative 3x2 plus 2x3 minus 2x5. We'll get that x3 is 1 minus 2x4 minus 3x6. And we'll get that x6 is 1/3. Okay, so now what we want to do is we want to try to take x6 equals 1/3, and we will substitute that in over here. So we'll use that x6 equals 1/3, and that'll help us rewrite. Let's see, x1, there's no x6 in it, so that'll stay. So negative 3x2 plus 2x3 minus 2x5, and for x3, that's going to become negative 2x4, because this negative 3 times 1/3 becomes negative 1, which cancels that 1. And we still have x6 equals 1/3. Okay, now what we could do is take x3 equal to negative 2x4 and replace x3. Okay, so we'll get that x1 is negative 3x2 minus 4x4 minus 2x5. We still have that x3 is equal to negative 2x4, and we still have x6 equal 1/3. And notice at this point our system is basically solved, because we've identified all of our free variables, and we've solved for all of our leading variables in terms of our free variables. So we just have x1 equal to negative 3r minus 4s minus 2t, where s is x2, r is x2, s is x4, and t is x5. We'll take x2 equal r, we'll take x3 equal negative 2s, and x4 equal s, x5 equal to t, and x6 equal to 1/3. So same solution as before, but what we did was we solved for our leading variables in terms of our free variables, basically doing more of a direct way of solving it in this sense with the back substitution, which might seem a little weird. Why don't we just keep going to reduced row echelon form? Well, sometimes this actually is easier for computers for some reason. Let's suppose that the matrices below are augmented matrices for linear systems in the unknowns x1, x2, x3, and x4. These matrices are all in row echelon form, but not reduced row echelon form. Let's discuss the existence and uniqueness of solutions to the corresponding linear systems. Okay, well, that first one right off the bat, look at that bottom row, that's a problem. We can't have 0 equals 1. What this basically says is that 0x1 plus 0x2 plus 0x3 plus 0x4 equals 1. So that's inconsistent. No solutions there. How about we look at the next one? We get 0 equals 0. 0x1 plus 0x2 plus 0x3 plus 0x4 equals 0, which is always true. Notice that means that we've got leading variable, leading variable, leading variable. There should be leading one over here. That is a free one, so we have infinite solutions, because that last variable could be anything. Okay, let's check out this next one. Looks like we just have x4 equals 0. So that's already solved, that's nice. But we have x3 plus 6x4 equals 9 from the second to last equation. Okay. So x4 is 0. So that means x3 is 9. Okay, cool. Let's look at this equation now. We have x2 plus 2x3 minus 4x4 equals 1. But I know x3 is 9 and I know x4 is 0, so that means x2 must be negative 17. And let's see if we can finish this. I know that my top equation tells me that x1 minus 3x2 plus 7x3 plus 2x4 equals 5. So I know what x4, x3, and x2 are. I'll plug all of those in, and I'll get that x1 is negative 109 when I simplify. Okay. There are 3 facts about row echelon forms and reduced row echelon forms that are important to know. Every matrix has a unique reduced row echelon form. We're not going to prove that, but it's true. Row echelon forms are not unique. So the reduced row echelon forms are, but the row echelon forms, there could be a whole bunch for one matrix. Although row echelon forms are not unique, the reduced row echelon form and all row echelon forms of a matrix A have the same number of 0 rows, and the leading ones always occur in the same positions. Those are called the pivot positions of A. The columns containing the leading ones in a row echelon or reduced row echelon form of A are called the pivot columns of A, and the rows containing the leading ones are called the pivot rows of A. A non-zero entry in a pivot position of A is called a pivot of A. So let's take a look at these row echelon form. Okay, we want to determine the pivot positions, pivot columns, pivot rows, and pivots of A. So those are the pivot positions first. So we have pivot positions. Well, those are going to be right over here. So it looks like we got 3 of them. we're going to have row 1, column 1, that's where our leading 1 is. We'll have row 2, and then it looks like it's in column number 3. And our next leading 1 is in column number 5 for row 3. Okay, how about we do the pivot columns now? Well, that's easy enough. We just identified what the columns were above. So that's just going to be 1, 3, and 5. Okay, we have a pivot position in each of these rows, so all 3 rows are going to be our pivot rows. So we have pivot rows are 1, 2, and 3. Okay, so now what are our pivots? Well, we have to look at where the pivot positions are. We've got them over here, here, and here. Well, let's go back to our definition for a second. The pivots are non-zero entries in a pivot position of A. Okay, so we look at the pivot position, we look at the corresponding entry, that's 0, so it's not a pivot. This 1 corresponds to -10 in the original matrix before we did the row echelon form. So -10 is a pivot. So we have pivots are -10, and we have one more pivot position. That was row 3, column 5. That was this leading 1 right over here, which corresponds to -5.